Okay, good morning, everyone.
Good morning, sir.
So finally, we had to work out our way this way only. We had to go online. I'll just be 1 minute. I have so many guests to admit. 1 minute. I'll just. We have 98 participants. Okay, now I'll start sharing the screen. Can you see my screen?
Yes,
Yes,
sir.
sir.
Yes, sir.
Yes, sir.
Okay, okay.
Yes, sir.
Good, good. I'm constantly admitting students. When will this stop? Okay, I'll keep doing this in between. Fine. We left here. The last thing which we covered was figures of merit, in which we discussed about coefficient of determination, and that value comes out from correlation coefficient. I think this was the slide, yes, where R is the correlation coefficient. So correlation coefficient defines what, and what we understand from correlation coefficient is how well the two variables are related, are correlated with one another. So that was what we did last time, and the value of R should range between 0, or rather ranges between 0 and 1. Since we square the correlation coefficient, therefore we say that it is on the positive side from 0 to 1. For general purpose, we consider 0.99 as the R square value, which suggests perfect correlation, and then one can go on to plot a calibration graph. And we know how we plot a calibration curve with our own values using using certain 1 minute. So this is how our calibration line should look like. Y is equal to y plus minus standard deviation of the y. and y is the measured variable, m is the slope and the deviation in the slope, measurement of the slope. Then we have x, which is the known variable, for a standard calibration curve. B is the intercept and SB is the standard deviation of the intercept. With this, we define the best straight line for any calibration curve when we go for any kind of quantitative analysis using any known equipment in chemical sciences. This is essential. So we need to represent our calibration line with standard deviation, which means essentially we need to repeat at least 4, 5, 6 times to bring out the best calibration line for our set of data. Then moving ahead, the next thing is, yes, this is where we wanted to start from quality control charts. What are quality control charts? Where they are used and why they are used. As it is written very clearly, a quality control chart is a visual representation of confidence intervals for a Gaussian distribution. What does this mean? This means that this is basically a chart, a display where one comes to know when you are analyzing a very large batch with large number of samples to see whether any of the points or the values which you record for your experiment is within the Gaussian distribution or not. So this is a visual representation. It can be seen on a monitor. All the analysis which are being done automatically, say for example, you have 100 samples in a batch and you cannot go and check each one of those because you are supposed to do the entire exercise within a definite time. So if this could be shown or could be seen on a monitor which displays in some form such that one comes to know whether any of those measurements, 100 measurements, follow Gaussian distribution or observe Gaussian distribution based on confidence intervals. So this is what is the control chart is. This chart warns us when a monitored property strays dangerously far away from an intended target value. For every measurements, of course, you have your average values. You have your average values. So, or the mean values. So how far the deviation of that value is, any particular value is from the mean, such that it goes beyond Gaussian distribution. That is what is the whole intention of having quality control charts. These charts are not used in our conventional labs. They are not used in our conventional labs. They are used in an industrial setup where you have large number of samples, different batches, 24/7. So one cannot check each and every measurement. So if this could be displayed on a screen, then one can easily find out and can take some preventive actions. Control charts can be used to monitor performance on blanks, calibration checks and spiked samples, which means again, these are different types of measurements. It can be used for blank measurements, several blank measurements, calibrations. Calibration checks means you can select a few QC samples. When we say QC samples means, see, calibration line will have at least 6 points, we know. Now, what is the quality control? Quality control are those selected points in a calibration line, which may not be same as the calibration line, calibration points, which may not be same as calibration points. They can be different, or rather they are different, but they are less in number as compared to the points which you use to prepare a calibration line. For a 6-point calibration line, you can have 2 or 3 quality control concentrations, which you can check periodically. So you need not have to recalibrate your equipment again and again through all those 6 calibration concentrations. That is what is quality controls, which are known as quality controls. Concentrations, which of course fall within the calibration line, but may not be the same as the calibration points. And spiked samples. It can be used for quality controls of spiked samples. Quality control charts can also monitor sensitivity or selectivity, especially if a laboratory encounters a wide variety of matrices. That is the case. I mean, this is a higher order of having display where quality control charts can be used to monitor sensitivity also, which as of now we don't generally use for measurements, but in some cases where the real samples have a very complex matrix, in those cases sensitivity or selectivity control charts can also be checked, measured. Now I'll just take you to the next slide where it will be clear to you what I just said. If you can see in this figure, what you find is you find mu, which is the mean, right? Which is the population mean. Now here it is population mean. This is the population mean. This one, this is known as the target line, or you can understand it to be the mean, which we expect the value. And above and below, what you find here is mu plus 2 sigma under root n divided by under root n. And on the next line, you have mu plus 3 sigma divided by under root n. N means number of observations. Sigma is the standard deviation. Now, our intention is that, and you can see corresponding lines in the positive side and the negative side. What they signify, this line signifies upper warning line. That means if any measurement goes between this point, this line and the next line, this is a region where you will come to know that, I mean, there is a slight deviation, more deviation in your measurements. Now, if you just consider it to be like this. So now this is your Gaussian curve. This is your Gaussian curve. This is how it will look like. This is your Gaussian curve. And this is, you can assume it to be 2 sigmas, and this is 1 sigma. So 3 sigmas. So this width, you can understand it to be 3 sigmas on the left and 3 sigmas on the right across this mean. And the spread of the values should be essentially between these two lines, the upper warning line and the lower warning line. So your spread of your measurement should be within these two boundaries. The other two boundaries, that is the upper action line and the lower action line, which suggests that if something goes beyond these two lines, that means it is going beyond the Gaussian distribution. And we know that around 95% of all the spreads in values is one moment. 95.5% of the values or the distribution of values is between these two lines, the upper warning line and the lower warning line. And 99% fall, 99.7% fall within these two lines, the top one and the bottom one, which is the lower action line and the upper action line. So basically what it signifies is, it signifies that it gives you a visual representation of all your measurements, and which is expressed in terms of your this thing, confidence intervals. Hello, please mute yourself. If you want to ask me something, you are welcome. But otherwise, please mute yourself. Okay, so this was something which was concerning quality control charts. And this is, as I said, it is not a conventional process where which you do in your labs, conventional labs. But this is for in an industrial setup where you have batches after batches, one after another, 24/7, which are analyzing, several hundreds and hundreds of samples, and where it is difficult to monitor their performance. So that performance measurement observation is done through quality control charts. This can be done for anything, as you came to know that it can be done for sensitivity measurement as well. It can be done for selectivity measurements as well. But that is a higher order of charts where the whole thing is that the values should be within the Gaussian distribution, that is 3 sigmas on the left and 3 sigmas on the right across a mean. Here mu signifies population mean, and then the others have their usual meaning. N means the number of observations. The next thing is standard addition technique. Now, what is standard addition technique? Where it is used, how it is used, how it is useful. These are certain things which we'll try to understand. And then, of course, at the end, we'll have one very small numerical to understand how one can use this technique for quantitative measurements. I'll just read this out for you. In standard addition, known quantities of analytes are added to the unknown. From the increase in signal, we deduce how much analyte was in the original unknown. This is the whole essence of standard addition technique. Standard means sample standard addition to an unknown. Now, the most important aspect is when you have any real sample which does not contain the analyte of interest to a concentration which can be measured by your calibration line. If the concentration is well below the, if it is well below the calibration line, one cannot measure the real sample, because once we have drawn a calibration line through standard solutions, the next step is to measure the unknown. And if the unknown does not have a concentration which falls within this calibration line would be of no use. And therefore, in such cases, we use this technique of standard addition, wherein we add that unknown, same unknown, but known unknown, standard solution of that into that unknown sample, such that the concentration of that substance increases to the extent that it can then be measured using that calibration line which you have established. Is it clear? અત્યાર સુધી ખબર પડે છે? I know it is a little bit difficult, but still, I hope things are clear. Anyone can tell me?
हाँ साहब थोड़ी थोड़ी पढ़े
थोड़ी थोड़ी
Yes,
पढ़े थे.
sir.
Just I want to be in touch with you because I cannot see you, and I just wanted to confirm whether તમને ખ્યાલ આવે છે. થોડું તકલીફ તો છે, I understand.
Hello,
But
sir.
still, yes, somebody wants to say something. Yes, please.
This standard addition point यानी इतना clear नहीं हुआ.
अच्छा, you are Kiran, right?
I am Saloni actually.
अच्छा, you are Saloni, but it is showing me
Yes.
Kiran Mishra. Okay,
Yes.
ठीक है, Saloni. I'll just quality control was fine. Quality
Yes,
control
sir.
charts.
Clear.
Okay.
From that graph it was
Sir,
clear.
hello.
Yes. Somebody
Hello?
else wants to say something. Yes.
Sir,
Saloni.
can you repeat it?
Which part? I mean, quality control charts or standard edition?
नहीं, standard addition technique. आप थोड़ा repeat कर दो.
हाँ, repeat करता हूँ. Okay.
Okay.
Sure. स्टैंडर्ड एडिशन का मतलब ये होता है कि अगर कोई रियल सैंपल में कोई अननोन जो हमें डिटेक्ट करना है या क्वांटिफाई करना है, उसका कंसंट्रेशन बहुत कम है, ठीक है. तो अब ऐसी सिचुएशन में हम क्या कर सकते हैं? या तो हम कैलिब्रेशन लाइन ऐसी बनाएं कि जो बहुत कम कंसंट्रेशन को भी डिटेक्ट कर पाए. लेकिन हमने एक चीज और भी देखी है कि ये बनाने के चक्कर में हम जो हायर कंसंट्रेशन है वो हमको सैक्रिफाइस करना पड़ता है. मतलब कहने का मतलब ये है, जैसे मैंने आपको एक बार लेक्चर में बताया था, हम एक रेंज बना सकते हैं 1 से 100 तक. मतलब कोई भी यूनिट होगा, पीपीएम में ले लो या पीपीबी में ले लो, 1 ppm to 100 ppm और 1 ppb to 100 ppb. तो तुम्हारा ये सवाल होगा, सर हम एक ऐसी रेंज बना सकते हैं कि जिसमें हम 1 से 1000 तक ले सकते हैं. Yes, it is possible, but not in all the cases. You are stretching this calibration line to the limits. जितने भी अभी तक दुनिया में एनालिसिस काम किया गया है, उसमें 1 to 2500 टाइम्स तक लिमिट बनी हुई है. बट दिस इज इन सम वेरी फ्यू केसेस. द जनरल लिमिट वुड बी एट लीस्ट 100 टाइम्स. 100 times तक it is manageable. Even up to 500 times you will find several papers or several methods which have a calibration line which can go up to, which is 500 times, that means 1 to 500. You can stretch the concentration to that extent. But beyond 1000, things become very, I mean, tricky, in the sense that there would always be an issue of reproducibility. That means when you stretch the method to its limit, naturally the results obtained would not be that much reliable. So there will be some other issues. So generally we don't go beyond 1000. That is one part of it. Having said that, in that case, if we have a very low concentration to be detected, naturally, I would like to go, say, for example, to 0.1 ppm, 0.1 ppm to 10 ppm. So again, it is 100 times. 0.1 to 10. So again, it is 100 times. So we cannot go beyond 10 in that case. But we can go down. So we have gone down, that is, we have reached up to 0.1 ppm, lower limit. So there is a limit to all the calibration lines. Now, if the concentration is very, very low, and you will find samples, there are so many samples which you will find which are having concentration very, very low. In that case हमको क्या करना होगा, हमको ये करना होगा कि हम रेंज तो ज्यादा नीचे नहीं जा सकते क्योंकि हमको रिप्रोड्यूसिबिलिटी के इश्यूज बहुत ज्यादा हो जाते हैं। तो हम क्या करते हैं कि उसके अंदर जो एनालाइट हमको मेजर करना है एक सैंपल में, एक रियल सैंपल में, वो उसका एक नोन सैंपल ले लेते हैं, स्टैंडर्ड सैंपल ले लेते हैं और वो सैंपल उसके अंदर डाल देते हैं, कुछ वॉल्यूम डाल देते हैं। जैसे ही उसमें डालेंगे तो नेचुरली उसका कॉन्सेंट्रेशन बढ़ जाएगा और जब कॉन्सेंट्रेशन बढ़ जाएगा तो वो कैलिब्रेशन लाइन में आ जाएगा। जब कैलिब्रेशन लाइन में आ जाएगा तो हमको ये पता चल जाएगा कि उसकी कितनी वैल्यू आई। फिर हमें ये पता है कि स्टैंडर्ड की इतनी आती है, इतने स्टैंडर्ड की, तो अननोन की माइनस कर सकते हैं। सिंपल, दिस इज हाउ स्टैंडर्ड एडिशन टेक्निक वर्क्स। सो बट इसमें भी ऐसा नहीं है कि आप कितना भी ले लो और कितना भी डाल दो। देर इज अ लिमिट टू इट, देर इज अ लिमिट टू इट। कि इसमें ऐसा भी नहीं होना चाहिए कि सपोज आपका concentration is say for just for instance 0.01 ppm अंदर सोल्यूशन ऑलरेडी है, ठीक है, 0.01 ppm सोल्यूशन है। तो उसमें अगर आपने 10 ppm डाल दिया वही सब्सटेंस नोन, तो ये कितना हो गया 10.01। अब 10.01 को जब मेजर करेंगे तो 0.01 तो उसकी एरर रहेगी, तो हमें पता ही नहीं चलेगा कि इसमें कुछ था भी या नहीं था। So it comes within that limit, prescribed limit of error for any measurement. 1 or 2% तो उसकी एरर होती है, तो वो एरर के अंदर ही आ जाएगी जो उसका अमाउंट प्रेजेंट था ओरिजिनली रियल सैंपल में। So there is a limitation to adding any standard to your unknown in standard addition technique. अब ये कुछ बात समझ में आई थोड़ी सी, मैं क्या कहना चाह रहा हूँ। There were two who were unable to understand. Saloni, is it okay now?
Yes, sir.
Okay. तो हम ये डालते हैं जब कॉन्सेंट्रेशन बहुत कम होता है, तब, पहले से नहीं डाल देते। और आप ये मेरे से पूछोगे आपको पता कैसे चलेगा ये कम है, कि ये इसमें कम है, तो आप कौन सी रेंज बनाए। अगेन एज आई सेड, जब कुछ पता नहीं होता तो you play with your experience, with your understanding, and therefore किसी भी सैंपल का सोर्स पता होना is first and foremost in any type of analysis. तो वो एक अलग चीज है, but this is how you use standard addition technique. अभी तो मैंने इसमें मैट्रिक्स की बात नहीं की है। अगर मैट्रिक्स का कुछ इफेक्ट हो रहा होगा रियल सैंपल में तो उसको भी अकाउंट फॉर किया जाता है, उसको भी अकाउंट फॉर किया जाता है। अब जैसे इसमें एक एग्जाम्पल है, उसको समझने के लिए what we will try to do here is we'll understand it through some values. Consider a standard addition in which a sample with unknown initial concentration, analyte xi gives a signal intensity ix. Then a known concentration of standard S, that substance is same, substance is added to the aliquot of the sample and the signal is observed for the second solution. That means एक sample था, उसके अंदर एक एनालाइट था X, लेकिन कम था, उसकी इंटेंसिटी मान लो के I है, उसमें हमने वही X का स्टैंडर्ड सोल्यूशन एक डाल दिया। अब क्या होगा, उसका इंटेंसिटी बढ़ जाएगा, बढ़ तो जाएगा, लेकिन जब आप कोई चीज अंदर डालोगे, एक लिक्विड, एक सोल्यूशन दूसरे सोल्यूशन में डालोगे, तो नेचुरल है कि डाइल्यूशन हो जाएगा, सैंपल का डाइल्यूशन हो जाएगा, और जैसे ही डाइल्यूशन होगा तो कॉन्सेंट्रेशन फिर से कम हो जाएगा। तो ड्यूरिंग स्टैंडर्ड एडिशन वी ऑल्सो कंसिडर द फैक्ट दैट the added standard gets diluted when it is added to an unknown volume. This is important. ठीक है? Addition of standard to the unknown changes the concentration of the original analyte because of dilution. और जिस प्रकार से जो आपने सोल्यूशन डाला वही एनालाइट का नॉन स्टैंडर्ड वो डाइल्यूट हो गया, उसी प्रकार से जो अननोन था जिस वॉल्यूम में, क्योंकि वॉल्यूम बढ़ गया तो वो भी डाइल्यूट हो गया, मतलब दोनों डाइल्यूट हो जाएंगे. कॉन्सेंट्रेशन वॉल्यूम डालने से कॉन्सेंट्रेशन दोनों के डाइल्यूट हो जाएंगे, जो अननोन था वही और जो नोन था वो, दोनों का डाइल्यूशन हो जाएगा. Let's call the diluted concentration of analyte XF, where F stands for final. This is how we try to understand this. We designate the concentration of standard in the final solution as SF. अब क्या हुआ कि जब हमने स्टैंडर्ड को एक अननोन में डाल दिया, यहां पे हमने डाल दिया, तो इसका कुछ वॉल्यूम डाला था, तो नेचुरली इसका कॉन्सेंट्रेशन चेंज हो जाएगा. जब इसका कॉन्सेंट्रेशन चेंज हो जाएगा तो दोनों का कॉन्सेंट्रेशन चेंज हो जाएगा, मतलब जो अननोन था उसका भी कॉन्सेंट्रेशन चेंज हो जाएगा और जो स्टैंडर्ड था उसका भी, और दोनों का डाइल्यूट हो जाएगा, कम हो जाएगा, और उसको हम कहेंगे, उस सॉल्यूशन को हम कहेंगे फाइनल कॉन्सेंट्रेशन, रिप्रेजेंटेड एज SF for your standard and XF for your unknown. अब ये एक फॉर्मूला है या एक्सप्रेशन है जिससे हम एस्टिमेट करेंगे कि हमारा अननोन था कितना ओरिजिनल. इसके लिए एक न्यूमेरिकल भी है. देखो, सिग्नल इज डायरेक्टली प्रोपोर्शनल टू एनालाइट कॉन्सेंट्रेशन. ये तो हमारी प्राइम रिक्वायरमेंट है किसी भी टेक्निक से. एंड देयरफॉर concentration of analyte in initial solution is equal to signal from initial solution, and at the same time concentration of analyte plus standard in final solution is equal to signal from final solution. हमारे पास सिग्नल तो इनिशियल के आएंगे और फाइनल के आएंगे, ठीक है, लेकिन हमने उसमें क्योंकि स्टैंडर्ड डाल दिया है इसलिए सोल्यूशन का वॉल्यूम चेंज हो गया, इसलिए कॉन्सेंट्रेशन भी चेंज हो गया. तो बेसिकली हमारे पास दो चीजें हैं. Concentration of analyte in initial solution is directly proportional to signal from initial solution, which is very obvious. लेकिन वो कम था इसलिए हमको उसमें ज्यादा डालना पड़ रहा है. Concentration of analyte plus standard in final solution is equal to signal from final solution because this is what it will measure. तो इसको अगर हम एक्सप्रेशन के फॉर्म में लिख दें तो कुछ ऐसे रख देंगे. xi जो अननोन है divided by XF plus XFF, that is जो फाइनल सोल्यूशन है, कॉन्सेंट्रेशन है X का, इसका वो XF हो गया क्योंकि डाइल्यूशन आ गया, और बाद में जो हमने स्टैंडर्ड डाला था वो स्टैंडर्ड था, लेकिन जब उसका कोई एलोकॉट डाला तो नेचुरली वो भी डाइल्यूट हुआ, तो उसको भी हमने XF से डिनोट कर दिया. सो दिस इज, and correspondingly this signal will correspond to which is coming only from Xi, and this signal corresponds to X and F combined because finally तो X is same as S. हम जो भी स्टैंडर्ड डालते हैं वो वही होता है जो अंदर होता है, जिसको हम डिटरमाइन करते हैं ना, वही चीज का स्टैंडर्ड सॉल्यूशन डालते हैं. So ultimately it is one and the same thing. The only thing is volume changes. Therefore देखो XF को निकालने का तरीका क्या था, ऐसे XF is equal to XI V0 by V, क्योंकि वॉल्यूम आ गया यानी वॉल्यूम करेक्शन लगाना होगा. XF निकालने का मतलब ये है XI into V0 by V, where V0 is the initial volume and VS अब जैसे लिखा है Vs is equal to standard volume of standard substance. So total volume would be V0 plus Vs. So this is your total volume. And likewise for your standard substance which has been added, this would be कितना लिया था, अब वो dilute होके इस फैक्टर से हमें पता चल जाएगा कि फाइनल कॉन्सेंट्रेशन वो जो स्टैंडर्ड डाला था, सिर्फ स्टैंडर्ड जो था उसका कॉन्सेंट्रेशन कितना हो गया होगा. दैट इज व्हाट हाउ वी अंडरस्टैंड SF एंड XF. अब एक ये प्रॉब्लम से ये सारा प्रॉब्लम जो भी है वो क्लियर हो जाएगा. Don't look at this. This is just the derivation of the previous equation which we just saw. This is where the problem. This is a simple solution, a problem and a simple solution to it. Now, the problem goes like this: serum containing Na plus gave a signal of 4.27 millivolts in an atomic emission analysis. As I said, this can be applied to any known instrumental technique or instrumental analysis. So what they are estimating is the concentration, the serum concentration of sodium ions using atomic emission analysis. This is a technique. This is an elemental technique which can be used for different elements. It is used for sodium, which is present in serum, and it gave a signal corresponding to 4.27. Then 5 ml of 2.08 molar NaCl was added to 95 ml of serum. 5 ml of 2.08 molar NaCl. That means NaCl is a standard. It will add Na to the existing Na in the serum, which gave a signal of 4.27. And then how much you have added? You have added 5 ml. To what volume of serum? Serum volume, which was 95 ml. मतलब आपने 5 ml को 95 ml serum में डाला, तो टोटल serum कितना हो गया? 100 ml serum हो गया. तो नेचुरल है 2.08 है, उसका कॉन्सेंट्रेशन कम हो जाएगा. दिस स्पाइक्ड सेरम जब हम डालते हैं ना किसी चीज में, स्टैंडर्ड हम उसको कहते हैं स्पाइकिंग. दिस स्पाइक्ड सेरम गेव अ सिग्नल ऑफ
लाइक कर गूगल पे लो જોઈ તર કીધું ખરી એમને રિયલ.
This spiked serum gave a signal of 7.98 millivolts. मतलब जो फाइनल एडिशन के बाद जो हमें सिग्नल मिला दैट वाज 7.98 millivolts. तो ये जानना चाह रहे हैं कि पहले कॉन्सेंट्रेशन सोडियम आयंस का कितना था कि जिसने इतना मिलीवोल्ट्स सिग्नल दिया. दिस इज व्हाट दे वांट टू फाइंड आउट यूजिंग यही इक्वेशन जो हमने अभी पहले देखी पहले वाले स्लाइड में. Ix divided by Is plus X is equal to initial concentration. This is what we want to find out. This is what you have added, and this must have been the result because when you add this, it gets diluted. So this is the final concentration of X. Now, if you look at what all values do we have with us? Of course, we have a signal corresponding to the sodium ion, which is present in the serum, which is 4.27. So that will be Ix. So you have written here. Then what you have is your Is plus X. So you have added once you have added, the intensity would be the combined intensity. So this intensity, what you obtain is 7.98 millivolts. 7.98 millivolts that you have written. NaI you want to find out. This is what you want to find out. But we can always find out the concentration of the diluted standard which you have added. Now this could be 2.08 multiplied by 5 divided by 100. That is the total volume. This is what we saw in the previous slide. So if you do this simple calculation, that means you are trying, because it will be less than this. तो 2.08 का इतना ml लिया था लेकिन उसको 100 तक डाइल्यूट कर दिया, तो कॉन्सेंट्रेशन कितना हो गया? 0.104. 0.104 is the concentration. So you have your SF to be this. Now we know that this x and this x both are the same. This is the in the original volume and this x in the final volume. So this x was in 95 and this x is in 100 xf. So just we need to put in the value of the volume correction, and that is 95 divided by 100. So if we know, otherwise it is xi only. So 95 divided by 100, if you write this value here, which is 0.95 into Na plus I. Why it is I? Because that it was actually, it is actually NaI, initial concentration, but it has been diluted. So this factor takes into account the dilution factor. So if you solve this, what you get here is sodium ions were 0.113 molar. So that is the concentration of sodium ions which was present initially, which gave a signal corresponding to 4.27 millivolts in an atomic emission analysis. ये चीज समझ में आई?
Yes, sir.
Okay.
Yes, sir.
गुड. ये बिल्कुल सिंपल सा सवाल है कि इसमें हम किस तरीके से डाइल्यूशन को कंसीडर करके व्हाट वी फाइंड आउट. जस्ट अ मिनट, वन मोमेंट. હેલો, હા બિપિનભાઈ. હા હું છું. હું તમને મારું લેક્ચર પૂરું થાય પછી હું તમને મોકલી દઈશ સિગ્નેચર. अच्छा. તો મારું 11:30 વાર પછી આવજો. 11:30 વાળા પછી 11:30 પછી. ઓકે. થેન્ક યુ. Okay, so this was all about standard addition technique. The only consideration was that you added that same unknown, same substance, but the concentration was known, and initially the concentration was unknown, and that is how. Now this approach can be applied to any technique. The only consideration is that the standard should be available for that. The known standard should be available for that, for any analyte which you want to measure in an unknown sample. The next is internal standards. What are internal standards? You just understood what is a standard addition technique. Internal standards का मतलब क्या होता है कि ये जो चीज होती है इंटरनल स्टैंडर्ड्स, इसका मतलब ये है कि तुमको मैं सिंपल वर्ड्स में समझाऊं तो कि जब भी हम कोई, एंड इट इज एसेंशियली यूज्ड इन क्रोमेटोग्राफिक एनालिसिस, जब हम क्रोमेटोग्राफिक एनालिसिस करते हैं तब किसी भी सैंपल की, तो एक अननोन चीज को हम एक कॉलम के अंदर डाल देते हैं. अब वो एनालाइट अंदर जाके कैसे बिहेव करता है, क्योंकि उसके बारे में हमें पता नहीं है. ठीक है, उसके बारे में हमें कुछ पता नहीं है, और कॉलम में अंदर जाएगा तो इंटरेक्शन होगा, कितना होगा, कम होगा, ज्यादा होगा, कितना देर तक होगा, बहुत सारे क्वेश्चंस हैं विच आर टू बी आंसर्ड, क्योंकि एक वो अननोन एंटिटी है एक कॉलम, और एनालाइट भी अननोन है. तो हम उसके अंदर जब डालते हैं तब अगर वो बाहर भी आ गया तब हमें ये नहीं पता चलता कि उसके साथ मतलब क्या हुआ होगा अंदर, इन द सेंस व्हाई इट स्पेंड सो मच टाइम, हाउ मच डिड इट इंटरैक्ट, हमें ये चीजों का अंदाजा कम रहेगा. तो ऐसे में क्या किया जाता है कि उसके अंदर हम उसके साथ ही अननोन के साथ ही एक ऐसा सब्सटेंस डाल देते हैं, एक ऐसा सब्सटेंस डाल देते हैं, एक ऐसा सब्सटेंस डाल देते हैं जो कि बहुत सिमिलर हो, which internal standard is a one which ideally mimics that unknown in every possible way. बिल्कुल उसको मिमिक करे, ऐसा कुछ डाल देते हैं ताकि जो हमने डाला है वो तो हम जानते हैं व्हाट इज इट, तो जो भी कुछ उसके साथ होगा, उसने ज्यादा टाइम लिया, कम इंटरेक्ट हुआ या वॉट एवर, everything will be similar, it is assumed to be similar, that must be happening with your unknown. तो इसके लिए हमें कोई दूसरा कंपाउंड डाल दिया हमने तो उसके साथ कुछ अलग तरीके से होने लगेगा, तो हमको वैसा कंपाउंड डालना है जो कि स्ट्रक्चरली भी सिमिलर हो, जिसकी फिजिको-केमिकल प्रॉपर्टीज भी सिमिलर हो, ऐसा कोई सब्सटेंस अंदर डाल दिया जाए along with an unknown, so that it can continuously track the movement of the unknown, and once it comes out from the column, if we can check whatever has happened to the internal standard which we have added, so same could be suggested for the unknown, that this is possibly must be happening with the unknown as well, because the internal standard which we have added is behaving in a way which would be very similar to the unknown, because they are structurally, chemically, physically, property wise, they are similar. That is what is. So the only difference in internal standards, these standards, and standard addition technique is, in standard addition technique you use that same substance. अगर सोडियम अननोन है तो आप सोडियम नोन डालोगे, लेकिन अगर इंटरनल स्टैंडर्ड की बात करेंगे तो अगर सोडियम अंदर है तो हम सोडियम अंदर डालेंगे नहीं, हम सोडियम का बिल्कुल सिमिलर कोई चीज डालेंगे which resembles sodium in as many ways as possible, so that whatever happens to sodium and whatever happens to that added standard, we can draw some parallel between these two. उसको स्टडी करने के लिए in such cases we add internal standards, and these are widely used in chromatographic analysis. इसमें भी एक numerical है, so that it will be things become very easier. इसके सिवाय एक चीज और भी होती है कि जब हम क्रोमेटोग्राफिक एनालिसिस करते हैं तो हमको सैंपल प्रिपरेशन भी करना होता है। तो सैंपल प्रिपरेशन जब किसी अननोन की करते हैं तो कभी किसी प्रोसेस में, किसी स्टेप में अगर एनालाइट को, अननोन एनालाइट कुछ हो जाए तो हमें यही पता नहीं रहेगा कि वो हुआ या नहीं हुआ। क्रोमेटोग्राफी तो बता देगी कि सिर्फ हाँ इतना था, लेकिन उससे पहले तो प्रोसेसिंग हो गई। सो देयर कुड बी सम चेंजेस during sample preparation as well, when we don't use, or rather in cases where we analyze, where we do analysis using chromatographic techniques. So in such cases a known standard of known concentration, which is not that same substance but very similar to that same substance, can be added. And the best known internal standard for any substance, unknown substance, is its deuterated standard, deuterated analog. अगर कोई भी deuterated analog अगर हम डाल देते हैं वही substance का, मतलब एक H हटा के D लगा के डाल दें अंदर हम, these are commercially available now, not for all, but for yes, there are many compounds. You will find they are deuterated standards. So deuterated standards work best because they resemble the analyte in as many ways as possible. तो अगर internal standard के साथ कुछ हुआ तो वही चीज unknown के साथ होगी, तो हम हमेशा जो भी रिस्पॉन्स लेंगे, रिस्पॉन्स विल ऑल्सो बी द रेशियो. तो रेशियो will always be the same. Fortunately for us, ratios will never change. So, and it is a dimensionless quantity. So that ratio is being measured continuously in chromatography and which is then used for quantitative analysis. तो ये एक बहुत इंपॉर्टेंट एस्पेक्ट है इंटरनल स्टैंडर्ड एडिशन का. इसमें लिखा if a known quantity of standard is added to an unknown prior to any manipulations, the ratio of standards to analyte remains constant because the same fraction of each is lost in any operation. अगर कोई चीज कम भी हो गई किसी भी स्टेप में तो इंटरनल स्टैंडर्ड का भी कम हो जाएगा, लेकिन हमें पता है कि हमने कितना डाला था, तो हमें यह भी पता रहेगा कि इंटरनल स्टैंडर्ड का कितना कम हो गया. इसका मतलब है कि अननोन का भी उतना ही कम हुआ होगा. But this is only possible when we use a deuterated analog. A deuterated analog or a labeled analog, मतलब labeled एक internal standard. And this is how we understand this internal detector generally has a different response for each component. अब ये जो चीज बता रहा है वो ये बता रहा है कि एक बहुत इंपॉर्टेंट एस्पेक्ट ये रहता है कि अगर आप ये मेरे से सवाल पूछो कि अगर हम क्रोमेटोग्राफी में कंपाउंड ए डालते हैं जिसका कॉन्सेंट्रेशन से 10 ppm है, एक कंपाउंड बी लेते हैं उसका भी 10 ppm है, तो दोनों का जो पीक आएगी तो एरिया अंडर द पीक क्या वो सेम होगा? नेवर. मतलब इट विल बी अ रेयरिटी कि दोनों का पीक एरिया सेम होगा. अगर कंपाउंड अलग तो इंटेंसिटी अलग, एरिया अंडर द पीक अलग. इतना ज्यादा डिफरेंस पाया जाता है ड्यूरिंग क्रोमेटोग्राफिक एनालिसिस. तो this thing is to be remembered that when we are trying to find out or estimate concentrations by adding internal standards, in that case the concentration has no bearing on the signal. Even for same concentrations the signals would be different. This is a very important aspect for separation techniques. अब इसमें लिखा है, for example, if both analyte X and internal standard S have concentration of 10 millimolar, the area under the peak might be 2.3 times greater than the area under the standard peak. मतलब स्टैंडर्ड का कम भी हो सकता है और ज्यादा भी हो सकता है. सेम होगा ये कोई जरूरी नहीं है. इसीलिए इसको हमेशा एस्टिमेट करने के लिए हम एक पहले से दोनों का, एक अननोन का एनालाइट एक्स का और एक उसका एनालॉग ड्यूटर एनालॉग जिसको हम इंटरनल स्टैंडर्ड एस कह रहे हैं, दोनों का स्टैंडर्ड सॉल्यूशन लेके एक हम फैक्टर निकाल लेते हैं. एक हम फैक्टर जिसको हम कहते हैं रिस्पांस फैक्टर. और रिस्पांस फैक्टर निकालने का फॉर्मूला ये है कि भाई दोनों में कितना डिफरेंस है. दोनों का सेम कॉन्सेंट्रेशन लेते हैं तो भी इंटेंसिटी दोनों की अलग आती है, तो वो क्या फैक्टर है, दैट फैक्टर विल रिमेन ऑलवेज द सेम. दिस इज व्हाट आई जस्ट वांटेड टू कन्वे, दैट दे आर टू डिफरेंट सब्सटेंसेस बट देयर response will be different even if they are of the same concentration. One will track, the standard will track the movement of the unknown throughout the process, throughout the analysis, throughout sample processing and throughout measurements. And for this the first step is to find out what is the response factor, how different the response factor is. तो इसको निकालने का फॉर्मूला ये है, area of analyte signal and concentration of analyte. मतलब ये जो अननोन वाला है, अननोन वाला. उसके बाद लिखा है area of standard divided by concentration of standard. अगर हम दोनों के एक सॉल्यूशंस बना लें हमारे पास पहले, before we begin our experiment, तो what we can find out is we can measure the area of that analyte जिसका हम एक नोन कॉन्सेंट्रेशन पहले से ले लें. दिस इज नॉट टॉकिंग अबाउट अननोन एट द मोमेंट इन रियल सैंपल्स दैट एनालाइट, बट उसका एक स्टैंडर्ड सोल्यूशन हम ले लें और उसका सिग्नल निकाल लें तो हमें सिग्नल पता चल जाएगा, कॉन्सेंट्रेशन पता है. इसी तरीके से जो हमारे पास इंटरनल स्टैंडर्ड है उसका भी हम एक कॉन्सेंट्रेशन ले लें, सेम कॉन्सेंट्रेशन, इट डजंट मैटर, और उसका हम इंटेंसिटी निकाल लें तो इंटेंसिटी पता चल जाएगी. अगर हम ये निकालेंगे तो इसका जो ये रेशियो आएगा, दिस ratio will be a factor which is known as a response factor, and it can be double, it can be triple also. मतलब इतना difference हो सकता है even if they are same concentrations and which are very similar in structure. That is what is first meant. Now in this, now we have a numerical to understand how we find out this. See, a solution containing 0.0837 molar X which is unknown, लेकिन पहले हम उसका एक स्टैंडर्ड सोल्यूशन लेंगे जिसका कॉन्सेंट्रेशन ये है, और एक हम इंटरनल स्टैंडर्ड डालेंगे जिसका कॉन्सेंट्रेशन है 0.666. हियर द कॉन्सेंट्रेशंस आर डिफरेंट, सो द रिस्पॉन्स वुड ऑब्वियसली बी डिफरेंट. रिस्पॉन्स वुड ऑब्वियसली, देखो यहाँ पे ये एक्स है और ये एस है, दोनों का स्टैंडर्ड सोल्यूशन ले लिया, दोनों का मेजरमेंट किया, पीक एरिया दोनों का अलग आएगा, इसका भी एक पीक एरिया, इसका भी पीक एरिया अलग आएगा. अब हमने ये दोनों स्टैंडर्ड सॉल्यूशन से हमने रिस्पांस फैक्टर निकाल लिया कि इसका रिस्पांस फैक्टर क्या है. ठीक है, अब सवाल ये है, टू एनालाइज द अननोन 10 ml of 0.146 molar S were added to 10 ml of unknown. अब 10 ml of unknown means हमारे पास एक X जो था ना, X which is unknown, लेकिन अब ये हमारा एक्सपेरिमेंट शुरू हो गया. यहां से हमारा एक्सपेरिमेंट है जो हम रियल एक्सपेरिमेंट कर रहे हैं. दिस मच इज योर एक्सपेरिमेंट. टू एनालाइज द अननोन 10 ml of 0.146 molar S was added to 10 ml of unknown and the mixture was diluted to 25. Naturally देखो अब इसमें dilute कर दिया वापस, यानी 2.5 times dilution किया है, तो concentration भी it will change accordingly. This mixture gave the chromatogram for which AX is area under X is 553 and the area for standard is 582. ये हमें दोनों का मिल गया. अब हमसे ये पूछा जा रहा है, find the concentration of X in the unknown. हमको एरिया तो पता चल जाएगा एक्सपेरिमेंटली, लेकिन कॉन्सेंट्रेशन निकालने के लिए हमें फॉर्मूला का यूज करना पड़ेगा. अब देखो, दिस इज द प्रॉब्लम, दिस इज द व्हाट वी डू. फर्स्ट हमको रिस्पॉन्स फैक्टर निकालना है कि दोनों के रिस्पॉन्स देने, सिग्नल देने में क्या फर्क है. तो देखो पहला वाला क्या था, दिस वाज द थिंग. पहले का एरिया आया इतना, ये लिखा है ना एरिया 423, और दूसरे का आया 347, और पहले का कॉन्सेंट्रेशन इतना था और दूसरे का कॉन्सेंट्रेशन स्टैंडर्ड का इतना था. तो देखो वही इन्होंने यहां लिख दिया, सेम थिंग 423 347, इसका कॉन्सेंट्रेशन ये और इसका कॉन्सेंट्रेशन ये, तो रिस्पॉन्स फैक्टर आ गया 0.97. अब रिस्पॉन्स फैक्टर अगर 1 आता मतलब सब कुछ सेम होता, लेकिन इसमें बहुत क्लोज आ गया है, जबकि कॉन्सेंट्रेशन बहुत डिफरेंट है, लेकिन रिस्पॉन्स फैक्टर इज वेरी सिमिलर, ऑलमोस्ट क्लोज टू 1. तो हमारे पास F की वैल्यू आ गई, F की वैल्यू आ गई, रिस्पॉन्स फैक्टर की वैल्यू आ गई. तो अब हमें क्या करना है, ये देखो वैल्यूज है स्टैंडर्ड का, अगेन दिस सेम इक्वेशन यूज करनी है. तो हमारे पास रिस्पॉन्स फैक्टर आ गया, AS स्टैंडर्ड का कितना होगा ये इन्होंने दिया हुआ है, स्टैंडर्ड डाला 10 ml 0.146, लेकिन इसको 25 ml तक कर दिया, मतलब डाइल्यूट हो गया 2.5 टाइम्स. तो उसका कॉन्सेंट्रेशन फाइनल कितना हुआ, वो इन्होंने कॉन्सेंट्रेशन निकाल लिया. 0.146 था, डाइल्यूट हो गया, 10 लिया था, 25 तक डाइल्यूट किया, तो कॉन्सेंट्रेशन कम हो जाएगा नेचुरली 2.5 टाइम्स. इसका कॉन्सेंट्रेशन ये हो गया, तो इसका कॉन्सेंट्रेशन ये हो गया, तो वो कॉन्सेंट्रेशन यहाँ लिख दिया, यहाँ पे दिस इज 0.0485. और जो सिग्नल आया था स्टैंडर्ड का, ये स्टैंडर्ड का ये रहा, दैट इज 582, वो 582 यहां लिख दिया 582. अननोन का स्टैंडर्ड का कितना सिग्नल आया था 553. तो x हमको निकालना है, x निकल गया, x comes out to be 0.0572 मोलर। लेकिन ये किस में निकला? 25 ml, लेकिन हमने अननोन कितना था? अननोन was only 10 ml. To analyze the unknown, 10 ml were added to 10 ml of unknown. तो हमने सिर्फ 10 ml में डाला था, तो 10 ml ये 25 ml का आया, यानी इसमें वॉल्यूम करेक्शन लगाना होगा। पहले 25 का जो इसका मतलब है जो कॉन्सेंट्रेशन है दिख रहा है आपको 0.057 से ज्यादा कॉन्सेंट्रेशन होना चाहिए, क्योंकि ये तो 25 ml में है, तो 10 में कितना होगा? सो इट विल बी मोर, so that comes out to be in this case you need to multiply it by 25 divided by 10. That is how, that is, it is simple n1 v1 n2 v2 जो आपको मैंने आपको बताया था, n1 v1 n2 v2, that 25 divided by 10 into 0.0572 which will give you 0.143 molar solution. So the concentration of the unknown in the given sample is in the 10 ml volume is 0.143, and this is what you could find out for quantitative analysis, and this is how you work with internal standards. किसी को कुछ पूछना है? मतलब is it clear?
Yes,
Hello?
sir. Yes, sir.
Yes, sir.
ठीक है, मतलब any one wants to ask, कुछ किसी को कुछ पूछना है? आज तो अभिषेक is there? I cannot see his name, but I can see Vishal, Ganvit, Anirav. There are people still waiting in the lobby. Okay. Saloni, Dhruvi.
Yes,
Saloni, you understood?
yes, sir. It's clear
इसको
now.
क्या है? Clear now. But you just once I'll send this PDF to you, I think things will be clear when you will see it for yourself. What exactly it has been done, how it can be done. But these are two very important. Yes, हाँ पूछो.
Sir, isn't standard addition is some sort of spiking, I guess?
Yes, exactly. Spiking.
Okay.
It is spiking. अच्छा देखो स्पाइकिंग का मतलब क्या होता है और इसमें क्या किया है, हम कहते हैं you spike the unknown with known standard. This is spiking. ठीक है. So this is one way of adding a known substance to an unknown. अब इसको ऐसा भी कहेंगे, अब स्पाइकिंग जनरली क्या होती है कि there is a limit to when you say spiking. अभी आपने लिया कि मैंने 10 ml ये लिया और 100 ml ये डाल दिया. That is not spiking. That is addition. Like you are adding to it. Spiking is something like when you use a volume which is not very large from the initial volume to which you add, and therefore you say it, you are just spiking it. You are not adding 10 ml में 100 ml. Understood, Dhruv?
Got it, sir. Got it, sir.
Okay. ठीक है, तो I think you have your second lecture lined up, right? Second lecture. I would now need about maximum 1.5 hours max to complete my syllabus. I just hope, and once I'll complete, and I hope to complete on Thursday, because Thursday I'll be getting, I think Parik sir would be finishing his lecture today. So whenever I get time, tomorrow I'm not free, but Wednesday or Thursday I'll just see if it is possible. I can wind up on by Wednesday or Thursday. Thank you so much. Thank you for your presence. Now you can, I think you are supposed to join, na? No. The other lecture? Okay.